Here's an interesting situation on a pulley system. We have a fixed pulley here, a movable pulley, a block of mass 4m attached here, a block of mass m resting on the ground. And this block A is 20 centimeters above the ground. Okay. Now the system, block B is released. The system is released from rest. Block A is going to hit the ground after a while. Block A will hit the ground after a while. We want to find out the maximum height reached by B. Now here's a little bit of a catch here. First of all, suppose the acceleration of this pulley was A downwards as shown. This point P is fixed, so acceleration of this point is 0. Now I straighten up matters here. So that B goes up around this pulley. So if I assume that B has an upward acceleration A1, then when I straighten it up, it will look like B has an acceleration A1 downwards. Now this gives me an opportunity to connect A, A1 and A2. A2 is 0 because the point P is fixed anyways, right? So very clearly A then is going to be A1 plus 0 by 2. Yes or no? A1 plus 0 by 2, right? So evidently A1 turns out to be twice A. A1 turns out to be twice A. That means if the acceleration of this is A, the acceleration of this is twice A. Now, what would you want to then believe? You want to then believe that if this goes down by 20 centimeters, this would go up by 40 centimeters. That is what you would initially want to believe, right? But you have to be a little careful about what exactly is implied in the question. True. The moment this hits the ground, 20 centimeters, this would have ascended by 40 centimeters, all right. Not an issue. But A sticks to the ground. A sticks to the ground, comes to rest after a while. After that, right? That's again claimed in the problem that after A hits the ground, it sticks to the ground, it doesn't rebound, right? But what happens to B? Block B, by the time it reaches 40 centimeters and A reaches the ground, B would have developed an upward velocity. So if B would have developed an upward velocity, B can rise up further. Now after B reaches a certain height, 40 centimeters, and this reaches 20 centimeters, if B rises up again and A stays in position, then the string will slacken. And then B will move purely under gravity. B would move purely under gravity. It would be under the influence of gravity. Yes or no? So if after a while, let's say when this has gone down 20 centimeters and B would have, let's say, moved up 40 centimeters, B would have moved up 40 centimeters, B at this point. So now, beyond this point, if B moves up but A stays on the ground, the string will slacken. If the string slackens means what? What's going to happen? Tension becomes 0. Now if tension becomes 0, and by this time if B has acquired a velocity V, then additional height that it's going to rise up to is going to be V square by 2g, because after a while its velocity is going to become 0 and it's going to be under the influence of g downwards. So it's going to reach a maximum height V squared by 2g above 40 centimeters. So then it would have come to rest at this point, right? Yes or no? And then what happens is it's going to fall down. The string will slowly and gradually begin to gain tension. And by the time the mass comes back to this point, the string would have become taut one more time. But what we need to find out is 40 plus V square by 2g. So V square by 2g, for that, in order to find the velocity it acquires on getting raised to a height of 40 centimeters, we would have to know the acceleration A1. Yes or no? Now how does one find the acceleration A1? So I need to find A, and therefore A1 can be obtained. I would have to apply equation of motion to A and equation of motion to B. Now as far as A is concerned, look, it has a downward acceleration A. So what then is the equation of motion for this? 4mg minus 2t is 4m into A, right? 4mg minus 2t, 2t here is 4m into A. That's the equation of motion for this. What about the equation of motion for this? T minus mg is m A1. A1 has turned out to be 2A, right? And I need to find the value of A. I'm not looking at tension. So what I do is I multiply this by 2. So I get like a 2T minus 2 mg is 4 ma. And when I add these two, 2T gets cancelled, right? Minus 2T plus 2T, and I have 4 mg minus 2 mg. That makes it 2 mg equal to 4 ma plus 4 ma. That makes it 8 ma. Or A is G by 4. A is G by 4. Yes or no? Right? So it has an upward acceleration G by 4. Now the question is, to get to a height of 40 centimeters, it takes a little while. It gets to a height of 40 centimeters. B, by the time it reaches 40 centimeters, it would have acquired a velocity V. How does one find this velocity? V square minus U square is 2as, right? Its velocity when it started was 0. Its acceleration is 2a. 2a means G by 2 upwards is its acceleration. Yes or no? 2a is its acceleration. A we have obtained is G by 4. So 2a is G by 2. So I can find V from here, right? V square is 2a1 into s, right? So V square is 2a1, U square is 0, 0 square plus 2a1 G by 2 into s, which is 0.4. Right? It's under the influence of an upward acceleration a1, which is twice a. So this gives me V squared equal to 0.4 G. 0.4 G, G is 10, so that makes it 4. V squared is 4, yes or no? Right? Now the additional height to which it will rise is going to be V squared by 2G. So what I can do is, I might as well leave it in terms of G. So this is like a 0.4 G. And how do I calculate this additional height? V square by 2G, because after this point the string will slacken, tension will become 0, and its acceleration would be G downwards. So if a particle is launched with a velocity V, to reach its maximum height, what would its maximum height be? U square by 2G, right? Its velocity becomes 0 at the maximum height. So V square by 2G, V square by 2G. So I need to calculate V square by 2G. What's going to be V square by 2G? V square by 2G is going to be 0.4 divided by 2, right? V square by G is 0.4 and V square by 2G is 0.4 by 2. That makes it 0.2 meters. Yes or no? That means now it'll get to an additional height of 0.2 meters, which is 20 centimeters, right? 20 centimeters is the additional height to which it gets to. 20 centimeters. So then what's the maximum height that it eventually attains? 40 centimeters, because by the time A reaches the ground, this fellow having twice the acceleration of A reaches twice the height, 40 centimeters. And then once it reaches 40 centimeters, the string begins to slacken. It's under gravity. Its velocity will reduce, it will become 0, it will reach a maximum height above this point, which is U square by 2G. So V square by 2G, and the way we found V is from 0 to V under the influence of an upward acceleration A. I have applied V square is U square plus 2A1S. So V square is U square plus 2A1, A1 is 2A, 2A is G by 2 into S, which is 0.4. So that makes V square equal to 0.4 G. Now this height is V square by 2G. So V square is this. So V square by 2G divide by 2G. G and G will get cancelled. So 0.4 by 2, that makes it 0.2 meters. 0.2 meters is like 20 centimeters. So the maximum height that it goes above the ground is 60 centimeters, not 40 centimeters. And a large number of you are prone to making mistakes here, because the moment you look at this problem, you would quickly come to the conclusion that, hey, the acceleration of this is twice the acceleration of this. So if this falls down 20 centimeters, you would inadvertently want to believe that this would move up 40 centimeters, and one of the options given in the answer would be 40 centimeters, and you'll fall for that. You'll get into that trap. And therefore, what you should do is, you should be calm about it. You should not stop thinking after this point, because by the time B reaches this point, it would have acquired an upward velocity which would further reduce, would raise it to an additional height V square by 2G. From here to here, the acceleration was a1 upwards. From this point onwards, since the string slackens, tension becomes 0. This is under the influence of gravity g downwards, this point onwards, and then it reaches a height v square by 2g above 40 centimeters, which we have computed as shown, right? So that's the whole idea, and therefore 60 centimeters is the maximum height to which it could rise. Makes sense to all of you, right? Bring you to terms with another pulley system. Movable pulley, fixed pulley, another movable pulley, and then there is a block B. What's given in the problem is that the vertical displacement, upward displacement of this pulley as a function of time is 1/4 t squared. That's given in the problem. Is 1/4 t squared, right? And we want to calculate the downward acceleration. The vertical displacement of A is given as 1/4 t squared. We want to calculate the acceleration of B. Downward acceleration of B. That's what we want to calculate. First of all, if y is 1/4 t squared, the upward displacement of this pulley from the ground, then could I have not written this as? Could I have not written this as half of t squared? So on comparing it with half of acceleration of A into t squared, very clearly acceleration of A then is half meter per second squared. Half meter per second squared is the acceleration of A upwards. Now let me come down to B. Let me come to this pulley first. So if I think about A, the pulley A, it has an upward acceleration AA, which we have obtained as half meter per second squared. This point P is at rest, so the acceleration of this point is 0. And if I straighten it up, if I straighten matters, it's as if this pulley will come down with an acceleration a naught. If I straighten up matters, it's like I take this string and I straighten it up. Then when I straighten it up, this point P will have a downward acceleration a naught. Now very clearly, acceleration of A is 0 plus a naught by 2. 0 plus a naught by 2. So that gives me an opportunity to compute a naught. A naught is twice the acceleration of A. Twice the acceleration of A, that means 1 meter per second squared, right? Now, if I know A naught, then I can compute AB. How? Because A naught is 0 plus AB by 2. So AB is like twice A naught. AB is like twice A naught, which is 2 meters per second squared, right? Yes or no? So then, what's the displacement, downward displacement of B as a function of time? The downward displacement of B as a function of time is going to be half of acceleration of B, which is 2 into t squared. That makes it t squared. That makes it t squared. Yes or no? Right? Look at this problem. This unit, this entire unit comprising a block A mass 2m and a block B mass 4m, and these two pulleys fixed to the two blocks with a force F acting leftwards. We want to be able to find the acceleration of the block B, given that these strings are light, inextensible, ideal strings, ideal pulleys, everything light, and these surfaces and all of the surfaces involved are smooth. Now, suppose this block has an acceleration a1 and this block has an acceleration a2. Let me first find a relationship connecting a1 and a2. So, the typical string constraint consideration, I assign this an acceleration a2. This is integral with a1, so I assign this point an acceleration a1. I assign this point an acceleration a1. Right? This point an acceleration a2, integral with the pulley. This point an acceleration a2, integral with the pulley, and this is 0. And of course, this is a2. And I traverse the string in this direction all the way to O, and I'll be able to connect a1 and a2. So I go this way along this segment, which is like a a1 minus a2. And then I go this way, which is like a minus a2 minus minus a1. And then I go this way, which is like a 0 minus a2 equal to 0, which is string constraint, So then we have A1 plus A1 2A1, and then minus A2 minus A2 minus A2. So that makes it 3A2. So that's one relationship. 2A1 is 3A2. Now, let me draw the free body diagram of 2M. What's the free body diagram of 2M? 2M, which is A. There is a force F acting this way, and this pulley is integral. And suppose the tension in the string is T. So very clearly we have T like this and T like this, right? And that results in an acceleration A1 of this, right? So the equation of motion for this is going to be F minus 2T is equal to 2M into A1. That's the equation of motion for this. Now let me look at 4M. What about 4M? 4M goes like this. There is the string, which is like T, and then there is this pulley, and there is T this way, and there is T this way. This is 4M, right? And this has an acceleration A2 leftwards. This has an acceleration A2 leftwards. So very clearly 3T is 4M into A2. Second equation. Ti eliminate. Ti I can write as 4M A2 by 3 here. So F minus 2 into 4M A2 by 3 by 3 is 2M A1. A1 I write as 3A2 by 2 by 2, which then leads us to F equal to, this is like 3M A2 and then plus 8M A2 by 3. A2 by 3. So that makes it 9, and it's 17M A2 by 3, which leads us to the value of the required acceleration, A2 equal to 3F by 17M. That's the answer. 3F by 17M, and that's the answer. Makes sense to all of you, right? Thank you so much. Bye-bye.